Welcome to a video for grade 12 physics. Today we're looking at Kepler's laws and how real non-circular orbits work. In the early 1600s, Johannes Kepler analyzed a bunch of astronomy observations and through careful calculations came up with three laws that describe the motion of the planets around the Sun. Kepler's first law states that planets move about the Sun in ellipses, not just circles. An ellipse is similar to an oval. Now, a circle is defined as a set of points where every point is the same distance from the center point. You can see in this circle, every point on this circle is exactly the same distance, 1 unit, from the origin at 0, 0 here. Now, an ellipse is defined as a set of points surrounding two internal points, or foci, focuses, where the sum of the distance from the points to the foci is constant. So an ellipse might look something a little bit more like this, where there are two focuses in here, and the sum of the distance from the points, both foci, are the same. So an orbit is an ellipse instead of just a circle. Kepler's first law states that the Sun is at one focus of this ellipse. Now, one thing to note, the more stretched out an orbit is, the more eccentricity it is said to have. So the further it's stretched out. Kepler's second law here states that a planet moves in its ellipse so that a line between it and the Sun placed at a focus sweeps out equal areas in equal times. Now, this is a little unintuitive, so let's take a look at how this looks in a simulation here. If we run this, we can see that the planet here is moving around the Sun. We also note the blue dot of the planet is speeding up as it gets closer to the Sun. The more eccentric the orbit, the more dramatic the speed up will be. You can also see that this planet is sweeping out a section of the ellipse. Each section takes the same time, and each section contains the same area. So the black sections and the white sections are all the same area. So this means that when the planet is closer to the Sun, it needs to move further along its orbit in order to cover the same area. So the closer to the Sun, or the orbited object a satellite is, the faster it moves. Now, Kepler's third law states the distance from the Sun to the planets is related to the orbital period of the planets by this formula. So here we have the orbital radius, which is r cubed, divided by the orbital period t squared. R is in meters and is measured from the center of the Sun to the center of the planet. T is in seconds and how long it takes the planet to go around the Sun. So for Earth, you'd need to convert 1 year into seconds for that. K is Kepler's constant. So Kepler's constant remains the same for every object orbiting the Sun. Now, that means that the Earth and Jupiter all have the same value for Kepler's constant. And for objects orbiting the Sun, Kepler's constant is 3.35 times 10 to the 18 meters cubed per second squared, kind of a weird unit. This does not hold true for objects orbiting a different object. So, for example, the Moon orbiting the Earth will have a different value, Kepler's constant. So, let's take a look at an example here. Mercury has an orbital period of 7.6 times 10 to the 6th seconds. First thing we can note is that this is already in seconds, and we have period here, and we know that the symbol for period in physics is capital T. I've already got this in seconds, I don't need to convert it. Determine the mean orbital radius. So in this case, we are looking for our radius, which is capital R, of Mercury. And for objects orbiting the sun, it gives us Kepler's constant already. So we have that already, which is excellent. So taking a look at this, our formula, if we start off by writing our formula here, we have R cubed over T squared equals Kepler's constant. Now I know that my Kepler's constant is 3.35 times 10 to the 18 meters cubed per second squared. I know that my orbital period is 7.60 times 10 to the 6th seconds. And I'm looking for my orbital radius here. Again, it's a good habit to get to writing down what you need off the hop. So starting to plug things in, I have my radius cubed divided by 7.60 times 10 to the 6th squared, careful about that, brackets there, equals 3.35 times 10 to the 18. Now, one thing to note here, right off the hop, I'm going to add in a note. I have a cubed here, so I'm going to need to cube root to get my answer, which is like that. Now, on your calculator, you may have a button that looks like this. That's the button you're looking for. Generally, on your calculator, you would enter 3 and then hit that button and then type in the number that you're wanting to take the cube. So, for example, cube root of 27 would be 3. That out. Okay, so plugging this all in, what I get here is I get my R cubed is equal to 1.93496 times 10 to the 32. I take the cube root of both sides to get rid of that cube there. And then my final answer, my orbital radius, is 5.78 times 10 to the 10th meters. Your question may ask for the answer in kilometers or another unit, in which case you'd need to convert that. But in this case, it didn't. So here is my final answer of 5.78 times 10 to the 10th meters, which works out to about 58 million kilometers. So this has been a look at Kepler's laws. You will see questions like this one where you'll need to use Kepler's third law to solve for orbital period, different objects. Just remember that this K value here is for objects orbiting the sun. Figure out a different K value for if you're orbiting the Earth or orbiting a different. Thanks for watching, and I'll see you in the next video.